longtime friend and colleague from Texas Instruments primarily. 20 years ago, Doug hosted and shared the PhysCom 92 and PhysCom 94 workshops that brought 100 people to Dallas to discuss the relationship between physics and computation. After these workshops, he started a PhD at UCD in quantum computing using geometric algebra, which Foster's talked like one here today. His PhD was awarded in May 2002. That work showed how computer science and algebraic approach to quantum science space using geometric algebra could give an interesting, insightful alternative to Hilbert space modeling. After leaving TI, Doug has been principal investigator for a set of roughly $1 million SBIR contracts that actually involved quantum computing. They connected neural and quantum computing using high-dimensional mathematics plus several other consulting contracts. Since the work was originally done, he has quite upgraded to symbolic computing. I think we're going to be hearing about that today also. The first upgrade was used Python, and the second was, again in 2012, a set of 20 disclosures and over 30 papers and presentations. And he's been a speaker for us several times in the past. We're glad to have him back. He's been working heavily with his co-author on this paper. I think the guy was also on your PhD committee.
Correct. Mike.
Nancy.
Right.
For the last 15 years. So let's give a warm welcome, if we will, to our speaker today, Doug Matzke.
Well, thank you all. Appreciate the great introduction. I'm glad to see everybody here. I know it started raining a little bit right an hour before, so glad you all made it anyhow.
Next slide.
Maybe you've seen the abstract if you've seen the announcement, so I won't spend a lot of time on that and with the great announcement, but we're going to talk about entanglement. And the reason why this is important to a computer science perspective is that people have known that entanglement and quantum computing in general is outside the scope of Turing computing. So if you're interested in abstract computer philosophy, then you have to be able to know that, and other people have been working on it, like Roger Penrose. So we won't go into that deeply, but just realize that this is a deep subject, and so as soon as you start looking at quantum computing and sort of information as the primitive information relationship between information and physics, then it's quite interesting, and that's part of what this story is today.
Next slide.
So in summary, we're going to talk about what is entanglement. It's qubits. Qubits is the smallest way of creating versus classical bits. It's a quantum representation using phase state to represent bits. And this is sort of like at the very bottom end, this is what you have to deal with in quantum physics. There's no NAND gates down there. There's just phase relationships, and we call this primitive operation a qubit. And if you combine those, you get E-bits. So we're going to talk about that. We're going to show you the math behind that. And realize that qubits and E-bits both is not classical computing. It's very different. And it's not part of the standard model. So if you're a physicist, realize that this is not normally talked about in the same breath as standard model. And so that's important to realize, and that's part of the novelty of what we're presenting. This paper, this work has come from, is we just self-published it in December on that website, taucornians.org, and you'll see where that name comes from in a minute. So first of all, realize that in order to have an entangled state, you have to have at least 4 dimensions. Well, in our normal dimensional space, we think of 3 dimensions and time, and even in a relativistic sense, it's 3D plus time as a 4D space. But this 4D space is different than that. So realize that quantum space-time is fundamentally different than classical space-time, and that's interesting if you're looking at primitive computational ideas. In fact, the motivation for using geometric algebra originally by Mike Manthey, who's been working on this subject at least twice as long as I have, is that he wanted to look at a computational approach to physics, or a physics approach to computation. And so he has a very deep rabbit hole of things to go talk about in that area, and I'm just going to highlight that, and you can go to taucornians.com and see a bunch of other older papers about that subject. But realize that most of the time physicists talk about it like Schrodinger wave equation. So they're thinking about this as probability amplitudes, as non-local waves. And the important aspect of that is that a regular classical wave diminishes with 1 over the square of the distance, right? But a non-local wave, like a quantum wave, it propagates in all directions. It doesn't diminish with distance. It's just there in all dimensions, and that's why quantum tunneling and all the quantum effects we see. So realize that comes from this high-dimensional property of quantum systems. Okay? Because of that, though, then this high-dimensional space has its own topological algebra and connections. And that's different than our 3D plus 1 space that we're used to, okay? Therefore, from our perspective in 3D space, it looks like non-local correlations. But it comes from the basis of this high-dimensional mathematics that is the basis for it. So just when you're talking about it, this is also called EPR, Einstein, Podolsky, and Rosen. Einstein didn't like quantum computing because of quantum mechanics because of that. But then Bell's theorem, John Bell eventually in 1960s, proved that, hey, EPR was wrong and Bell's theorem was right. And so one of the things that we know is that we're going to talk about here is quantum entanglement is really going to be very pervasive. And we're going to argue that it's stable because due to the irreversibility of it. And that's some novel results from both my PhD and from this work. So quantum entanglement underlies, we know, quantum computing, Shor's algorithm uses entanglement. We're going to introduce this 3D plus 1 tau Quernian space, which is entangled. We're going to introduce this notion of a Higgs field and Higgs boson. This is the representation that people use. This is like the little Higgs field, and that particles that going through it essentially create mass by how much they attach to the Higgs field. So that's the view that classical physics have of this, where this is here a part of the quantum ether. Even in empty space, it's all full of this, and the Higgs field is pervasive. So we're going to talk about the Higgs field and the Higgs boson, and we're going to talk about what we call dark bosons and dark matter as well, and we're going to show that that's also entangled. Okay?
Next slide.
So again, what is the definition of entanglement? Well, first of all, it's only quantum systems. It's non-local due to the high dimensions. That's the EPR, the Einstein spooky action at a distance, and we're going to show you the Bell operators. There's a particular mathematical property called inseparable quantum states. And think of it from a Boolean algebra perspective. If you can't factor common terms out, that's called inseparable. And quantum systems have a very known, well-defined thing for inseparable quantum states, and that's what they are. And it turns out these Bell and magic operators, which we'll show what those definitions are, we found that in the Hilbert space they are reversible, but in the geometric algebra they're irreversible. And this is a fundamental difference because it turns out that the geometric algebra is another representation for the same, supposed to be the same isomorphism, but yet it has a slightly different prediction about it. And then we go look at the mathematics and realize that Hilbert space actually has additional dimensions that it's not using, where geometric algebra is more like a pristine version of what those dimensionalities. So it makes a slightly different prediction, and we think that's important in this particular case. And so the key idea is that qubits, multiple qubits, acting as one e-bit, that's really what entanglement is. Iconically, we show that as a qubit is two orthogonal dimensions like this, and then we're going to show an e-bit as two bivectors, and you'll see in a minute, and this is the representation for bivectors.
Next slide.
Okay, we're doing this work is in geometric algebra, and the key thing that geometric algebra has, it has vectors just like regular Hilbert space does, but it also is very aware and cognizant of a thing called bivectors, trivectors, and in general n vectors, where n can be, we usually go from 0 through 4, and then multivectors are sums of these primitive components. And the way you can think about this is if you have a and b vector like this, the spinner is the right-hand rule spinning out like this, and so this AB is orthogonal to both A and B, and it's a bivector. So again, here's an iconic way of looking at that. And if we call each of these terms singletons, and in G0 there aren't any vectors. In G1 there's one vector, represented by A here, vector A. In G2 there's two vectors, A and B, but there's also the product of A, B, which is this spinner. And this is a fundamental aspect of geometric algebra. And likewise for G3, you have all these terms. So you have trivectors and you have four vectors. Okay? And notice how the size is squared of the number of terms before that. And so realize that we're essentially doing computer science exploration, data mining of a 43 million state space here. And that's what we're doing as part of this computer science approach to geometric algebra. Okay? One of the things to realize is that this is an anti-commuting vector space. So it looks like Boolean algebra, which is good. Hey, I'm a computer science guy. I like to look at things that I'm familiar with. So except for this one thing is that it's anti-commuting. And what that means is since it's anti-commuting, if you take two of these terms, you square it, and you multiply it out, and then you reverse A and B, which changes its sign, and then the A's cancel and the B's cancel, you get -1. So any bivector is really the square root of -1. It's a spinner. So this shows that bivectors are an inherent high-dimensional version of imaginary numbers. So now you realize, oh, anything that we can do with imaginary numbers, we can do with geometric algebra, and that's true. Okay? And then we use arithmetic operators plus, and we'll show you what that means. Just regular multiplication, but it's the geometric product. And in this algebra, you can think about it as equivalent to the tensor product, but it's really a formal definition of a sum of the inner and outer products, where, as you'd expect, the inner product, if two things are aligned, they're 1. If two things are orthogonal, they're 0. They're orthogonal. So the inner product is test if it's the same, and outer product is the thing that says it says if it's different, then I'm taking an area essentially. So it's a bivector, and same thing for other things. The other thing we're going to introduce is co-occurrence, and we show that with a plus, and we co-exclusion, where two things, if they subtract and equal to 0, that means this 0 means it does not exist. So you cannot have this state and this state simultaneously. But if this state is observed in the system and this state is observed in the system, that implies that there must be a spinor AB, because this is a rotation of that. So this is a formal mathematical definition of these properties. The other thing that we found in this, everybody knows what a truth table is in Boolean algebra. Well, we did the same thing here. We created, and I'll show you an example in the next slide, but every algebraic form of an equation has the equivalent of what we call a row vector. Think of it as a diagonal of a matrix if that helps you, but think of it as a vector of all the states, and we'll show you where that comes from. It's a true duality. You can go from one to the other and back, and it's isomorphic, and it's one-to-one mapping.
Next slide.
Okay, so we built these geometric algebra tools. Originally we did it in Perl. Now we've done it in Python. And so the key thing about this, it's mod 3 addition. So we're representing plus and minus 1 as the two binary values, plus and minus. So what we're doing is we're separating 0. 0 means doesn't exist, rather than 0 meaning false. And this is a great semantic improvement over Boolean algebra. Very important distinction. And so some of the key insights come from understanding that we separate the two binary values from the does not exist value. Think of it as tri-state logic, if you want to think about it that way. So what we find is if we have this is actually the result of my symbolic interpreter I've written in Python. I have a binding of A, and it's bound to a vector A object, and if I add them using operator overloading, we get minus A. So A plus A equals minus A. This is the kind of thing that you'd expect in topological algebras. Okay? And likewise, you can see the anti-commutative behavior. Normally, we always show all vectors and bivectors in a normal sorted order. So what happened is I've entered in a bivector in the normal order, and it resorts it and prints it back out, and you can see there's the minus sign. Same thing true. It does this for all trivectors as well. Also, if you take multiplication, you can not only do addition, you can do multiplication. And as you would associative and commutativity, if you take an expression like this, it actually expands this out. And if you think about this, this is the row vector for that is this state. Notice there's only one plus there. So think about this. If this was a Carnot map and I needed to have only one cell in a Carnot map addressed, I'd have to use every algebraic term in the system in order to address and eliminate all the others except that one term. Same thing is true here, and it contains all algebraic terms. So it's easy to generate all the terms for the algebra like this. So then we've defined a single qubit state as like A0, just so that we can have multiple qubits. And we say the classical qubit qubit A is in this state where the plus and minus means it's a classical state. And I'll show you what that means in a minute. And so then we can say, here's the spinor. We've defined a symbol called SA to be the spinor bivector. If we square the bivector, we get the square root, we get 1. So the spinor is minus 1. And if we multiply the spinor times the qubit state A, we see that this is now a superposition version of the same qubit, and that's what you would expect for. And the quantum register is just A times B, and you can see this is the normal. If you were to put this in Hilbert space as a Brockett notation, it would look virtually identical using the Brockett notation. Okay? So, and here's where this truth table comes from. We've created this function called GA states, and what it does, given an expression, it goes in and says, if A is minus and B is minus, what's the output, what's the value of this expression? And it says it's plus. And there's rules about how we do plus and minus, but it's just basically Boolean algebra with Z3 arithmetic for addition. So if you take this output column, that is that row vector. I call it a row vector because it's the state of all these rows. and it's the vector form, and now we've built that into our tools. So we can go in and say, report to me in geometric algebra 2, a 2 version of AB, here's the row vector, here's the equation, and here we're going to talk about this in a minute, here's the bit content equivalent, and here's a complexity measure of that. And so we can go in, remember I said up here we were showing you A times addressing the smallest addressable item. Here again, here's an example with only 4 items, and you can see that it expands out. Here's that. And also, if we take 2 terms, here's the plus and plus, here's the same one above here, and here's the minus and minus. And so if we add those 2 together, notice we see that has 2 terms instead of 1 term. So these terms are linearly independent of each other, and that's an important consideration as we move forward. And everything always is in a standard form. You never have to do synthesis or optimization on the Boolean algebra because it always expands to the common form in this system.
Next slide.
So we're going to talk about this idea of co-occurrence and co-exclusion a little bit because it's related to what I call space and time proto-physics. I'm calling it proto-physics because it's more primitive than conventional physics. And so we have identified the plus as this co-occurrence. And it means 2 things have to be simultaneous to interact. If they can't interact, then they're not in the same subspace, if you want to think. So as soon as we say plus, it means that they think of it as a relativistic space. They're next to each other in space so they can interact. So we use that as a plus operator. And likewise, the co-exclusion is an abstract time. If you have this state and later you have this state, then some operator must have occurred. Think of it as a time-like operator, that some primitive change occurred due to an operator. So plus and multiplication, addition and multiplication, have a specific meaning in here from a very primitive time and space perspective, which are computational concepts. Space and time are an important part of what we do with computation. But we find out as well from people like Rolf Landauer and John Wheeler that information is physical. They know that in computing, that if you erase information, you must account for it. You can't just ignore it. And in fact, the pièce de résistance of that is that if you throw a bit into a black hole, it must change the black hole. And it does so. The smallest discrete increment that you can change a black hole is a bit, and it's Planck's area and its surface area. So physics and information theory are intimately tied together in black hole physics, but also in computation in general. Reversible computing all came out of these kinds of ideas, and black hole mechanics finally solved this problem over the last 20 years. So these are important concepts to realize that this, again, is a deep subject, a rabbit hole of subject areas.
Next slide.
So I'm going to demonstrate what I mean by space and time primitive. This is a favorite demo of Mike Manthey. He calls it the coin demo. So imagine there's a person standing in front of me, and he shows a hand, takes a hand off, and he shows you this coin, okay? Okay? And then later on, he hides that coin and then shows you another coin. And it's indistinguishable. Think of them as tokens, okay? So the question is, how many coins do I have? I've sequentially showed you potentially 2 different coins, but no matter how fast I do that, you still don't know how many coins I have. So if you got an answer to this question, you would have received 1 bit of information. Since we know you can't just create and destroy information, part of this puzzle is where did that information come from?
Next slide.
So now I'm going to show you that the Act 2 is the person actually shows you a hand that shows 2 identical coins. So therefore, we receive the 1 bit of information since this ambiguity is resolved. And the question is, where did that bit of information come from? This is part of this non-Turing information perspective of quantum computing. And the answer is, it's the simultaneous presence of 2 coins. So remember I was showing you co-occurrence before is plus. Essentially, co-occurrence, simultaneous presence of 2 anything, is fundamentally different, and somehow that's an information, there's an information content differently than the 2 pieces itself. We refer to this as a non-Shannon space-like information because a Turing machine and Shannon information style way of thinking about this doesn't include this kind of information, the simultaneous presence of 2 things. Turing machine is all about sequencing. Well, it doesn't talk about this, even in a multi-head case for Turing. So we call this non-Shannon information, and this is part of this whole question about the fundamental difference between space and time and information. So it comes from that simultaneity.
Next slide.
So now we're going to shift gears back again. We're going to go back to these algebraic forms. We call these a multivector, and we're going to add, here's the row vector, the equivalent row vector for that, using that truth table stuff that we did before. Plus 1 is just like the diagonal of a matrix. You'd expect that to be, and minus 1 is the same way. 0 you can think of as zeros all in there. Okay, so if I add these two, one of the things that's really cool about this representation, they're linearly independent. So literally I can add these two columns and these two columns and these two columns, and plus is minus and plus and minus is 0. And so literally now I can do, it's kind of like Fourier analysis, you can do summing of frequencies easily. In this representation, you can do linear sums of these kinds of things easily, and you can get this other state. One of the things we can notice here, if we count the numbers of zeros, the complexity of this, are these two things the same complexity? Well, I would count the number of pluses and minuses, and then what we do is we actually sort them. So we sort them, and we have 0, 4, 4, because there's 4 of one kind, 4 of the other kind, and 0 of the third kind. There's 0, plus, and minus, okay? So we can see that all of these forms, even though I've added or subtracted scalar from this, you see that we call this a complexity measure. It's a signature. It says that these 4 terms all have the same complexity measure. In other words, they have the same expressive power in a Carnot map as each other. They could be transformed in one another. So what we do is we take this complexity signature, and then we say, okay, we can go compute it for all of our spaces. So we can go and say, well, how many signatures do we have? And we have 3 of them, the scalars. And how many complexity measures in G1 do we have? And it turns out this is the signature, and it's forms for vectors x and plus and minus x, okay? And we can then take, there's 9 total, and so 3/9 taken to 9/3. It's the probability of this occurring randomly, which is information theory, and we can find out that this is equivalent to 1.58 fits. And likewise, a vector state, if this was randomly occurring states, it would something that fell into this bucket would be equivalent to 0.58 bits. It's more common, so it has lower information content, right? This is a standard definition of information content. Well, we've done the same thing to G2, and we found out that there's 4 buckets in G2 instead of only 2. And we find out that we actually see the coin demo coming right out of this. If we have singletons, there's 18 total of here, and they have, each one of those has what we call 1 singleton in it, and that's what this is. And so the information content is 2.17 bits. Likewise, there's 36 variations of this signature, and the information content is 1.17. Well, if you subtract those, that's 1 bit to an arbitrary number of decimal places, because these are exact counts. And so as a result of that, we actually see the coin demo information content come right out of these statistics, which is kind of both surprising and interesting. So one of the things we've done is realize that as we get to higher algebras, we want to use this, what we call the singleton count, the structural complexity, and so we've gone in and added this column over here and added that to the tuple space, and now we can go and compute the same thing for G3 and G4.
Next slide.
And as you can see, here's an example over here where this 4 here, you can see that it's the same complexity. They both have 0, 4, 4, but one of them has only 1 singleton and the other one has 4 singletons. So this way we can differentiate between things that are similar to each other, and that's the whole purpose of this. And we find out that a lot of these counts, because it's plus and minus x of this form, all things are double of the other ones. So what we find is a 1-bit relationship here between like 2.29, 3.29, 4.29, 5.29, 7.29. Everything's off by 1 or 2 or discrete number of bits. So we do the same thing for G4. This is a particular interesting computation over here, this one here, is because this is 43 million states. It took me like a month of computing time to compute this, the exact counts of all of these 43 million states. Part of what we're doing with the data mining is still going and looking at all these properties of 43 million states. And the way we're doing that is by using these signatures, and we can find out what things are complexity-wise equivalent to each other. And this will come in later on in a minute. You'll see where this information count comes in. We did this for this work in the last year. And this is kind of really applying computer science to what physicists would normally not think about doing. So this is an interesting outcome of this work.
Next slide.
So we're going to step aside for a minute. We're going to remind everybody what's so different about qubits. And we're going to start with, and this is going to be a crash course here. If you really want to understand what we're talking about with qubits, then go read my dissertation. I mean, it's 200 pages where I basically showed that geometric algebra in G2 is exactly equivalent to a qubit. There's nothing left over, nothing missing. Okay? And that was the proof that we did, and it also showed entangled states. So geometric algebra is a useful way of thinking about quantum computing.
That month of computing time for G4, what kind of machine was
Yeah, it was just my laptop, but it was, I've done it multiple times, so I've done months and months worth of computing time to do this. So a regular classical bit is, you can think of them as mutually exclusive, that state 0 and state 1, if I sum them, they cancel to 0. So they're mutually exclusive. This is what we mean by mutually exclusive, where a qubit here is what's called spin 1/2. Think of it as half as much. It's only 90 degrees, but these two states are orthogonal. What that means is that I can add them together, and normally the way that that's done in regular Hilbert space notation, Brockett notation, they sum these two vectors, where these two vectors are orthogonal. Okay, and so this is the Hilbert space representation for that. Here's our representation for it, where these two states are opposing, so they're classical. These two are either the same or the same plus or same minus. So these are the two superposed states. And if you take any one of these terms, multiplied times the spinner, it changes it to the other term. And then, so you can see, this is the regular qubit algebra expressions for spinners. So this is a brief introduction to what a qubit is and why it's different than a classical bit.
Next slide.
So if you take those now, we have these spinners, and if we take the spinner for A and the spinner for B and we sum them, what we're saying is, I want simultaneously spinning for A and B. That's what the plus means here. I get this expression here. This is virtually identical to the form of the Bell's and magic states that you would see in the Brockett notation. They also show them in other representations like this, that they sometimes show them with arrows. But this is the Hilbert space representation for it. And as you can see, the representation that we have is virtually identical, knowing that it's just in a vector notation rather than this Brockett notation. Again, here's the symbolic representation of it. Well, what we found in geometric algebra, because of the symmetry of it, is that you take that operator and you multiply it times any state, and you get what's called the Bell state. And this is equivalent to one of these Bell states. And if you multiply that Bell state times the Bell operator again, you find out it's a ring, and you end up back to your 0. So this is the formula for the Bell operator, and this I did during my dissertation. And this is just mathematically beautiful, and it's a much cleaner representation in geometric algebra than it is in the system over here for the Hilbert space, because of this nice ring behavior that it has. Also, you can do the same thing with the magic state, and all the magic state is the same thing with this minus sign here. It's a phase conjugate of the Bell state, and you get the phase conjugates of all these other states. So it turns out that the sum of all of these Bell and magic states is the total list of all the unique entangled states that are the sum of two bivectors in G4. And so what we find is you cannot factor this as inseparable, just like it is in Hilbert space. And we find, this is the one unique difference from Hilbert spaces, is that the proof that 1 over SA plus or minus SB, there does not exist an inverse for this. So it's irreversible. And that's the one thing that came out of the dissertation, that we now understand what that means in geometric algebra. One of the important things about why this is important is because if we erase information, it's irreversible. Well, this actually has information erasure. If you take two qubits, it is nothing more than the sum of these four states. That's the exact same representation that you'd have in Hilbert space. But if you factor these out, you realize one of them is a Bell state, one of them is a magic state. And if you realize that multiplicative cancellation, if you take any of these Bell states and you multiply them times anything over in the magic states, they equal to 0. This is multiplicative cancellation, so you're erasing information. So this is a key thing that we can hang our hats on, saying this is real science, and it means something, and that's what we're trying to build on here. So it's an important result.
Next slide.
So what are the tauquarnians? Now, we created this term tauquarnian as a sort of a jumble of the normal quaternions, the term a quaternion. A quaternion is just a mathematical way of representing these three dimensions using what's referred to as the quaternions. Usually they have I, J, and K notation for it. But if you look at it at an X, Y, and Z location, they are really bivectors. So hey, one of the things working in geometric algebra, you realize what things are vectors, what things are bivectors, what things are trivectors, and that really helps you sort out the zoo that you're working with. Okay? One of the things we realize is that tauquarnians, and we're going to show you what they are an entangled version of quaternions. And here's the set of those. Here's the first set, and here's the dual basis set. And as you can find out here, these two first terms, the T sub I, this one's the Bell state here, and this one's the magic state. So one of those, the Bell and magic state's in there. And they anti-commute. If you take any two of these, they anti-commute. This is a property of quaternions. And they sum to -1. And here we had to be creative about what does -1 mean. It turns out it's a sparse version of -1. And as you'd expect, if you take -1, square it, you would get something called +1. And we also have a sparse version of +1. And as you would expect, +1 times +1 squared is equal to +1. That's what's referred to as an idempotent. So we do have that same property here. The difference is it's sparse. Here's the -1 state. And notice you can see it has all minuses in there. It's very symmetric except for the 0 state. So it's a sparse version of -1. And here's a sparse version of +1. And then there's duals of each other where the zeros go to minus and the minuses go to 0. So there's a dual version of those. And so that's looking at the row vector version of that. So once you realize that, you go, well, here's the formula. We have Tx times Ty is equal to minus Tx. So there's this property and if we decipher that, we realize, oh, here is that table, and that's the definition of a quaternion. That's why we know that these tau quaternions are quaternion isomorphs, because this is the same definition as a quaternion. So if we then say, well, what are all the valid sets for this? Turns out that here's 8s using magic as T sub I, 4 that use magic, and 4 that use Bell. Here's the formulas, and we'll show you why we think it's these sets. And then if you take minus T sub I, there's another set where the minus signs are switched. Okay, and we're going to show you that one of the things that this is all related to is both this definition of space. We're saying space itself now can be built on entangled states. Hey, nobody's ever said that before. And we're also going to show that this is related to the Higgs, which we're leading up to in a minute here. Okay?
Next slide.
So how do we know in this algebra what things are particle, what things are bosons? I mean, a physicist would care about this, right? Well, we know because in our algebra we have a determined number of states. So we can do data mining on it. So we can find all the bosons in G3 by just using this function I wrote, which is gsolve, and it iterates through all of the permutations of the parameters. And it says, given a function, lambda where I'm taking x squared, it had better equal to 0. So I just run this program, search the space, and I find, hey, there's eight things that are nilpotent in G2, and there are none in G0 and G1 except for 0. We're going to represent, this is important from a physics perspective, because in G2, there's one set of structural things that all have the same complexity measure, x plus xy, and we are identifying those as the weak force bosons. And we'll show you where we came up with that conclusion in a minute here. And then we go to G2, find out there's 5 sets of nilpotents in G2. And these are all of them, and we've identified this as the photonic boson. Again, there's the weak force version in G3. There's more variations of it, so there's 24 items here instead of only 8, because there's A, B, and C to substitute in for X and Y. And then there's the quaternion itself is bosonic, and we identify these other things as a mesons and a gluon. And just as a comment, we're thinking the quark is X plus or minus X plus or minus YZ, but it's not bosonic. But the sum of 2 of those things are a boson. So that's where we think the mesons come from. And so likewise, we can do the same thing. Notice there's 7,280 total unique things out of the 43 million that are bosons. And that's what we're doing, is we're data mining. And we're finding out, hey, we have identified an important critical item here, W plus XYZ, and we're going to identify this as a dark boson, and we're going to show you it's a very simple primitive boson in G4, one of the simplest ones besides the ones that we already know about from the earlier sets. And notice there aren't that many. We're talking about 5, 6, plus 30, 36 different structures total. So we can exhaustively look at them. And one of the ones that comes out of this is we're going to identify as the Higgs boson, and we'll show you that in a minute. So one of the things to realize that G3 is equivalent to the Pauli algebra. G4 contains the Dirac algebra. And also, you look at this as discrete items, but realize that Parseval's identity applies to all of this. This is all vibrational modes. You can think of them as processes that are sequencing through, and they are generating sequences of things, and you can think of them as vibratory modes. So realize this is all, it looks discrete, but it's all frequency at the same time, like time domain and fast Fourier transforms are isomorphs of each other. So just realize, again, this is a very deep subject. in an hour we can't talk about all that, but I'm just kind of giving you pointers about some of the way we're thinking.
Next slide.
So the other thing that we did is we quickly went and says, well, tell me where all the particles are in the system. And all the particles we can define as where x squared is equal to 1. They're unitary. And it's easy to do this. And I mean, I can show people if they want to see, I can run things for G1, G2, and G3 in literally minutes. But you can just see all I've done is substitute for x squared is equal to 1 instead of x squared is equal to 0. And if you do this, now you get, in G2, you get two items. You get the vectors themselves, and you get this form here, which we're going to identify as neutrinos. They're particles, so we know they have to be a particle, and because it's unitary. And likewise, we can go into G3. Again, we find only 4 here. Some of them are neutrinos again, the vectors again. But now we see electrons and protons. So out of all of G3, what we're seeing is, so far we have all of the primitive stuff, and we have quarks defined in G3 as well. We have all of the primitive stuff of what we would consider the standard model. Well, this is interesting because it topologically shows that that's the more primitive stuff in the universe. And we're going to show you in a minute here at the end how the universe evolves from G1 to G2 to G3 to G4. And then you'll say, oh, well, that's important that we know sort of what grade these particles come from. Okay? So finally we get to G4, and there's 12,690 total expressions of 43 million that are unitary, and we're identifying some of these again as the vectors and the mass carrier. So there's a total of 17 different signatures that are unitary. And one of the important things to realize is that, and mathematicians don't usually think about it as concisely as this, but if you have x squared equals x, which means it's idempotent, and u squared is equal to 1, which is the definition up at the top, unitary, then x is equal to minus 1 plus or minus u. And all you have to do is do this math yourself. It's easy. You just take x squared, multiply this out, substitute u squared equals 1, and solve it, and you get x again. So realize that as soon as you have identified where the particles are, you've also identified all the idempotent stuff in the algebra, and there is a one-to-one mapping about it. On a finer note on this last item down here is that if you try to rewrite this u is equal to some version of x, you find out that there's an asymmetry built into that, and we think that maybe that has to do with why particles versus antiparticles are dominant in the universe. So even some small things like a little proof like this may have some insight about some of the asymmetries built into the universe. So I've been using this example of talking about bosons and unitary particles as a way of justifying, well, how did we get to these answers? How did we get to this insight? And one of the things that's important is to say, well, we kind of this is the standard model. If you go to Wikipedia and you look at standard model, this is the picture they have here. And this is sort of a great summary. Everything on the left 3/4 here is the fermions, and the bosons are the red ones. And as you can see here, we've identified the bosons. We've already identified this column here. Those were all the nilpotents. The squared is equal to 0. And we've identified the weak force bosons, the gluon, and the photon. Okay? And those are primarily in G3. Okay? So remember we said here's the neutrinos? Well, the neutrinos, this column over here, this column here says that there's 3 of them. Okay? And it's the electron neutrino, the muon neutrino, and the tau neutrino. So we do the math and we say, well, there's really 4 of them. If you look at this algebra, the row vector has 4 items in it, and the topological structure looks like this. So if you look at it, you realize there's another one. But one of the interesting things is that if you sum 3 of these together, you get another one back. So it may be that neutrinos are really hard to measure. It took them a long time to even detect all of these 3 types. It may be that there's a 4th type, a transformational equivalent, and we just haven't measured it yet. So this is a prediction that we don't know what it means yet. Hey, we're not physicists, but we're just looking at the topology and saying, hey, this might be something interesting to go look at. It's like for a long time, they only got 1/3 the amount of neutrinos coming from the sun they expected because they couldn't measure the other 2 neutrinos, the solar mass neutrinos problem. So this is a puzzle that says, hey, maybe there's these little 2 red boxes here form that structure. But we both have the particles and the antiparticles. So you have the right count. That's the key. For every one of these things in this left 2/3, the quarks and the leptons, you have to have both the particle and the antiparticle version of it. And we're going to show you that the particle and the antiparticle are inverses of each other. So that if you add them together, they go to 0. So they can't occur at the same time. So if you take an antiparticle and particle and you collide them together, all the information is erased, and that energy goes somewhere. So that's our model of where antiparticles from. So we have the antiparticles. Likewise, we have the electrons, and we have the exact same count here again, except that because we have both E, and then we have a phase dual version of E, where this is a plus here and a minus here. So we have twice as many as we should, kind of like we have an extra one up here, and we have twice as many here, but otherwise everything else holds together as far as its property and its structure. Notice this is G3, so you can't get electrons until you have G3, but you can have neutrinos in only G2. So finally, the quarks come here and realize that when we do quarks, you end up with this mapping, and one of the things that we believe that you have to do is instead of going from Z3, you have to go to Z5 because you need 2 ups, 2 downs. To get all the quantum zoo that you see, you have to be able to add more than just one item of something. You have to be able to add 2 of items. So then it may be that you go to plus and minus 2, plus and minus 1 and 0 as the prefixes, that you're allowed that range of context to do that. But essentially the counts all match up, and it has the right structural properties, and we can see where it gives us insight. I mean, nobody else has this is the formula for electron. Most of the other stuff that physicists are doing, well, except photons. Photons, they say, hey, it's a Q-trit. You know, they know that a photon is probably a Q-trit. Okay, but nobody else are they saying, this is the formula for electrons and neutrinos and quarks, because they're all doing transition matrices from particle accelerator stuff. They don't actually have the formula for it, okay? It's all this transition matrix stuff. So, I mean, we're just hoping that, hey, by producing this out here, maybe some guy who's a physicist says, well, this makes sense from what I know, da-da-da-da, and then we can work with physicists who are interested in this problem.
Next slide.
So that was a little digression from where we really were, but we wanted to show you that, hey, we really can have something insightful to say about the standard model. So then later on when I say the Higgs and entanglement isn't part of the standard model, I can substantiate it because I know what all that stuff is, okay? So what we've now done is we're saying the proposed Higgs boson, which we've identified back 4 or 5 slides before, is just the sum of these tachyonians. We've taken the sum of 3 of these tachyonians, which was that table we showed you was 4 and 4. Why did we have that table? All we have to do is take all the permutations of these tachyonians, sum them together, and when their square is 0, then it's a boson. There's 16 versions of that. There's 8 of this form, of the T sub i's, and then there's some primes, 8 more of those, okay? Well, what we can find out is once we've done that math, it's really easy to identify what those are. I've listed them in that other table, in the tachyonian page. But we can also refactor those because this form here, this H is equal to the sum of those. It's just the sum of 6 bivectors, 2 at a time. And they're entangled. Okay? So we can refactor that by remultiplying it. We find that it looks like light, a time-like mass acting on space. This is this version, where this is the quaternion. AB plus AC plus BC is the quaternion. We showed that. That's bosonic. And we also showed that we think A plus B plus A, B, C, D is the mass carrier. And so this looks like general relativity. I mean, it's a variation of general relativity, a refactorization of relativity. You can also refactor this so it looks like light, A, B, C, which is a Q-trit, and space. This is the quaternion again. So you see light and space simultaneously. Also, we know that Higgs is its own antiparticle, and so we have an extra 8 versions of the space where we use minus T sub I instead of T sub I. Okay? So this is what the form looks like for the Higgs, and we can formally define there's 16 of these that where x squared is equal to 0. And it has an additional property where x is of this form times ABCD is a rotation in 4 dimensions, and it equals to the ABC rotation. Remember, these things are anti-commutative, so the fact that this is a 4 space here and I'm doing a rotation, it means it's commutative. And it also is equal to itself, a plus or minus version of itself. So that's a very specific definition of what we think the Higgs is. And oh, by the way, what are those other 48 states where they do not equal to 0, where it turns out that x squared is equal to A, B, C, D? Well, we think these are 2 kind of variations of protomass, and we actually find out there's 2 versions of them because they have different signatures. That means they're out of phase with each other, and they have different state spaces defined by it. So not only do we have the Higgs, but we have 2 variations of what we call protomass, and all with the same formula. And that's, again, we're data mining the state space and characterizing the space. And that's what this means. So now we've defined that these entangled states that are from quantum computing, not part of the standard model, And we see that they can create space where they are equivalent to the Tauquirnians, so that Tauquirnians are an entangled version of space, and the sum of those Tauquirnians, 3 of them, add up to a Higgs, which is a boson, and it has those properties that are very interesting. Now we say, well, what about variations, rotations of these entangled states? So that's what we're going to talk about next.
Next slide.
Turns out here's this state, Wx plus Yz, that's an entangled state. If I rotate it by 3 dimensions, x, y, z, I get this state now that's a single vector and a trivector instead of 2 bivectors. And likewise, I can reverse it. So here's an iconic representation of it. I take 2 bivectors that are orthogonal, and I turn it into a single vector and a trivector. Well, what's interesting about that is if you do that, this is what you get. And you do the same thing with the magic states. There's the entire population of all the states. And if you square them, they're equal to 0. So they're bosons, and it's one of those primitive bosons we've discovered, and they're inseparable because you can't separate those. So they're entangled. And so when you start looking at dark energy and dark matter, this is the current belief about the amount of dark matter and dark energy that has to be in the universe in order to see galaxies form and things like that. And so the atoms are really only 4% of the matter. So you go, how come there's not more regular matter? Where's all this dark energy and dark matter we can't see? Where is it? Okay. Well, what's interesting about this is we find that the quarks has this form, W plus XY, and these dark bosons, we could say maybe these dark bosons are the dark energy, but we don't really know for sure. All we know is that they're a boson, and we're going to show you in a minute why it's related to dark matter, that has this form. So this is interesting. It has a very similar topological structure, but it's in one more dimension, okay, than the quarks do. And it's in a 4-dimensional space rather than a 3-dimensional space, okay? So what we end up seeing is that the dark bosons are in an odd subalgebra of G4, and the entangled regular conventional Bell and magic states are in the even subalgebra of G4. And in fact, we'll show you that it's the entire even subalgebra of G4 that the entangled states occupy, okay? Especially with this formula here.
Next slide.
So what we're going to do is we're going to show you now, since quarks, what did we do with quarks? We took 2 of them and made mesons. We took 3 of them and made protons, right? That's what the definition of a quark is. Well, we took Tauquirnians and these entangled states, and we added 3 of them together to get a Higgs. It's kind of like quark-like addition. Well, what we're going to see now is that if we take these dark bosons and we take 4 of them and add them together, this is what we think is dark matter. So it's kind of a building block the same way that you would use quarks to build other particles. Here we're saying dark matter is really, there's 256 of this because there's all the some variations of this. And we find out it is the largest odd subalgebra of G4. There's nothing left over there. And this is the formula I was looking for a minute ago. If you take the dark matter definition and you rotate it by x, y, z, you get that you end up back in the entire even subalgebra of G4. This is important because it says that you can go back and forth between regular matter, at least the Higgs states and the entangled states, and dark states, which are also entangled. You can go back and forth with them with rotations, and they're equivalent to each other. It's not, you don't destroy anything by doing that. It's a reversible operation. So that says that you can go back and forth between them, and that all these entangled states are built on quantum computing. They're built on entangled states, okay? So this is the message we wanted to get out, and this is part of the reason I'm here today to talk about that. So if you take these d squared, now we're going to say, well, what are these d squared? They're entangled, sums of entangled states. It turns out they form 3 or 4 subsets depending on how you count it. If you take a subset of this, and we're going to call those d sub q for quaternions, their square is a quaternion. It just ends up with that. And it turns out the likelihood of that happening is this signature and this bit content, and the count is 128 of the 256. Likewise, there's a subset of these that are 32 of them where their d squared is equal to 0. So they're bosons. So here we have a dark version of matter that's the sum of these that are also bosons because their d squared is equal to 0. And we'll see in a minute that this bit content is really low compared to anything else in the space. And likewise, we have another one where d sub u, which is we identified as 2 qubits, and it's d to the 8th power is equal to 1, so it's u for unity. This is 2 qubits. There's 96 of those. And there's 2 variations of this, one with 5.3 bits, 80 of those, and 16 of this other one. So there's 2, we've identified 4 versions of dark matter, potentially, with different topological structures. So again, we're just data mining this stuff and finding out these properties. So maybe this is important to a physicist to know that, hey, there's maybe 4 kinds of dark matter out there. So we're going to tie all this together here in a minute by showing you sort of like, well, we got the information content, we got these entropies, the bit content of these states. We know where the bosons are. We've done the exploration. We think we've identified some of these as being the properties we care about. But where does all the energy from the Big Bang come from?
Next slide.
So that's sort of like how we're tying it all together is, and this is important because if you're trying to look at the evolution of the universe, you have to have a story that is an entropy-driven story about how the Big Bang happened, right? And so that's what we're trying to do here. So what we say is if you have G1, you just have a single vector floating out there in whatever subspace you want to think about. It just doesn't have much distinctive power. It just says, hey, I have 1 bit. And you know that a vector is equivalent to 0.8 bits in this state. So all you have is, this is the entire algebra you have, is plus or minus 1, plus or minus a. But all of a sudden you go to G2. What did you do to get to G2 to G1? Well, you took 2 G1s, you combined them together, be a co-occurrence. Now all of a sudden you have plus or minus A and plus minus B, where before they were like separate. So all of a sudden you've gone from 2 one-dimensional things to 1 two-dimensional space. And what's the difference between those two? Is that they actually interact. So there's this interaction. And when you do that, the interaction creates this AB. Well, what is AB? It's just the product. So you have addition and multiplication. You have plus the addition of 2 vectors together. That's a non-Shannon information release. And the multiplication creates new n vectors. So all of a sudden you're populating your higher dimensional space with this unique combination of the individual vectors that you already have. The sum of all of these states determines the information count of that space. Okay? And so what you're doing is your complexity is increasing as you're going up this hierarchy, and pretty soon you have the same thing. You have G3 and G4. Notice where something that had 0.58 bits before is now worth 18 bits, 18.9 bits. Well, where did that information come from? Well, it can only come from one place. It can only come from the zoo of singletons that populate our space, and those can only come from the addition and multiplication operator, which is the primitive time-like and space-like operators that are part of this topological algebra. So all of a sudden, this is the beginning of a story, and here you can see that this is a 4-dimensional version of a hypercube, and that's not 3-dimensional space. This is a 4-dimensional space topologically, very different than 3D plus time space. So this is the basis of where we think it's really a bit bang. It's this bit information coming together of these dimensions, and that entropy is it's creating these new distinctions, these new algebraic forms. They combine together in a compound space that's increasing complexity, and that increasing complexity using non-Shannon information release kind of like it releases that information somehow, and that fuels, if you're destroying due to multiplicative cancellation and that kind of thing, that information has to go somewhere. You can't just say, it's gone. It's released as energy, it turns out. And that's this energy that's fueling the Big Bang. So this is right out of black hole theory, okay? This is not something I'm just making up. It has to be consistent with black hole theory. Otherwise, black hole theory, you couldn't get entropy and information and quantum mechanics and gravity all tied together in a black hole. It just wouldn't work. So this is again a deep subject, and they've made a lot of progress in the last 20 years on this. So what ends up happening is you end up with where eventually these dimensions are more primitive than the regular classical or relativistic space-time, and as soon as there's enough matter and energy and space and time created, then you actually have the Big Bang occurring. Before that, it's the Big Bang. There's no even time before that. And so we believe that this is the process where this fuels where this energy comes from. Purely comes from a purely information theoretic perspective of this topology.
Next slide.
So we can summarize all this in one grand big table, and it looks like a lot of stuff, but remember we were talking about complexity. This arrow here for the complexity is the same arrow that was on the previous slide. We're going from G1 through G4, and what we can see is here we have higher entropy is the green stuff. Those things are highly likely. So if you have a primitive universe and you only have G1, which is this area right up here, that's all there is, G1, all you can see is I've got 1.75 bits, and I've got this section here. That's it. That's the entire topology that you have. So what do you have in G1? You just have vectors, and you have the beginning of neutrinos, okay? In G1, you don't even have, you just have vectors. By the time you get to G2, now all of a sudden you have neutrinos, qubits, you don't even have qubits until then, and you have the beginning of the weak force. And the green ones here are the ones that are highly likely. So if things were just randomly being combined, those are what you'd expect to see populating the universe. And likewise, if you go to the next one here, the green ones again are the highly likely ones. So all of a sudden what was highly likely in G2, all of a sudden you go to G3 and you realize it's more likely that something else is going to be more likely than that. So as things start interacting and evolving with addition and multiplication, all of a sudden you're finding out that the EMF and the gluons and the photons and the protons are highly likely just due to the information count. Just due to that they're highly likely to occur. So all of a sudden G3, you're seeing things that are really primitive, neutrinos and qubits. All of a sudden you're seeing the standard model stuff evolving out of the entropic development of the universe naturally due to this information count. Okay? And so likewise, you can go to G4, and G4 is so big, I'm just going to another chart, but you see the things that are most common here are, again, this EMF force. You think of this as, they see this as two versions of gluons. I have a gluon down here, this version of a gluon. Well, remember, gluons are bosonic, so there should be G squared equals zeros. Well, it turns out of all of the gluons, there's a lot of gluons, highly likely that gluons will be done in G3 and G4, but there's another version of this gluon that we call the EMF force, and its squared does not equal 0, so it's not bosonic. So we're predicting that there's like not only a bosonic version of a gluon, but a non-bosonic version of a gluon that's related to EMF carrier, where we see ABCD. We see AB as the spin carrier, ABCD as the charge carrier, and ABCD as the mass carrier, and that's what we're going to see in the next chart here.
Next slide.
Here's the continuation of this same slide, and on the paper, this is all one big table. And what's important here is that these are the most likely states. Remember, the smallest information state in this was 3.09 bits. And these states down here, which is the dark matter, are highly likely. They're 5.53 bits, 6.87 bits, so, only 4 times less likely than the most common state. A 1-bit difference here is twice as less likely, okay? And likewise, you see that the Higgs is 7.08, so it's just slightly above the dark matter and dark energy, but it's highly likely, and one of the protomasses is highly likely as well. These are some of the lowest things, and by the way, all those things in red are entangled states. They're the population that's part of the entanglement that is the substructure, what we think of space, gravity, dark matter, and dark energy are all related to these entangled states. And they're highly likely. Now, individual states aren't very likely. They're 10 bits difference between that and the dark matter. So it's 1,000 times less likely that the individual entangled states individually exist rather than being bundled as part of something else, if that makes sense. So remember that these dark matter and dark energy and the Higgs are all just sums of those. So they tend to want to aggregate right away because it's entropically driven to do so. And it releases the non-Shannon information associated with that. And so we go one more and we realize that there's these outliers. There's a version of the protomass that's not very likely, 13.1 bits, and a version of dark matter that's also not very likely, 15.9 bits. So you probably won't see those very often because they're not very likely by randomness. Even finding the Higgs itself isn't very likely compared to, just because of the energies involved too. I mean, this is all just based on information theoretic views of things, okay? So you can see that this is a nice story, and it kind of matches with what we're seeing in an evolutionary story of a Big Bang and a Bit Bang, and it kind of makes sense. It kind of follows that same story. So again, we are interested in getting this story out to say, is this a useful paradigm for physicists to look at, okay? So how much time do we got here?
Down to virtually nothing.
Okay, so this is the last slide.
Next slide.
I'm going to just point out a couple of the novel conclusions and some predictions, okay, that we made in this paper. First of all, we say geometric algebra is a useful paradigm to do this with. And if you look at non-Shannon space-like information, the coin demo, and it kind of supports that, hey, we're looking at very primitive space-time information mechanics process. Think of it as physics as computer processes. And one of the things we've done is we've done data binding of these nilpotents, the idempotents, the unitaries, and we think we've identified a lot of useful things for the standard model, especially in G3. We've completely identified G3, everything G3. There's nothing left to unidentified. So if something is in G3, we've already identified it. Now G4 is another story because there's a lot of them that are mostly sums of other things that are entangled. So, but we don't know what those are yet, what they mean, but we've also predicted like there's potentially 4 neutrinos, okay? We know that this result of irreversibility of Bell and magic states is a fundamentally sort of different. And one of the things that you need to know about reversibility is once you go into that state, you've erased it, you can't get out again without adding that information back in. So it's stable. So it's not like you can just rotate out of it and says, oh, it's gone now. No, it's stable. That's the importance of the irreversibility of entangled states, because all those entangled states that are behind the Higgs and all of the dark matter and these dark bosons, those states are stable because there's nothing interacting with them, and they can't get out of it because it requires information being added to it. So we could think that that would be a stable basis for the evolution of the universe. That is a really important distinction to say that they're irreversible, because it makes a different prediction than if you didn't do it. Once we know that, hey, all these E-bits are out there, we can say, oh, hey, we can build entangled 3 spaces. So that's why you all of a sudden realize, oh, 3 space isn't topologically local. I mean, now all of a sudden the space itself can support entangled phenomena. You can create these 3 space entangled, and that is the basis of the Higgs field, we think, and the proposed Higgs boson. And that's all the even subalgebra. But if you go to the odd subalgebra, it's a rotated version of the Higgs, the dark bosons, and the 4 forms of proposed dark matter. I like this picture of the jelly beans. That's a picture of the dark matter in the universe. And then finally we say, due to the signatures and bit content, hey, we have a bit bang, and we think we have a pretty good story for why that is true. We want to remind people that our version of particle and antiparticle, they're co-exclusion. So we brought that up early, but they sum to 0, again, which is an information release, not due to multiplicative cancellation, but due to addition cancellation. They're just literally canceling each other out. So that energy has to go somewhere, so then the energy formula says, hey, it's released as a photon. And then conclusion is entanglement pervades everything, space, the Higgs, the dark matter, and that stuff is not standard model, and it's not classical. So this is a new perspective, a novel perspective of why the Higgs is so hard to work with, and and why the dark matter's, it's odd. If you can't see the dark matter, how come we can't see it? Well, it's all the odd grade stuff, and everything else in the universe is even grade stuff. So, it's a prediction that's out of phase with respect to the regular matter that we see. It still has a gravitational effects, which is why we can measure it. We can see its lensing effect on distant galaxies and stars. But entanglement pervades everything in this. And it's more common than we believe by just looking at the standard model. And that's the important conclusion. So thank you for your attention today. Hope you find this as interesting as I do. And I'm willing to take questions, or we can come up and afterwards later on and ask more questions. Thank you.
Any questions for Doug?
I know it's a lot of stuff, but realize that the full paper is like a 45-page paper is out there on tokornians.org. I'm working on even what I would say a variation of the paper that's sort of more of like step-by-step. Like if you didn't know anything about geometric algebra, it's sort of like designed after this talk, but we're working on a different paper that's like, and we're going to put a YouTube video of this. I'm going to take this talk and put a YouTube video up there as well of this talk using the voiceover in the slides. So we'll have a YouTube version of this project as well. Go ahead.
A suggestion.
Yes.
That to make it a little bit easier to follow, is to show what operations in geometric algebra are that you are analogizing to operations in space.
Okay. Well, remember that this is the sort of like data mining view of the state space, and also realize that the state space in the Hilbert space, they have the row vector notation of the Hilbert space, the Braquet notation, and then they also have the matrix view, which is the operator view. In this geometric algebra, every sub-expression is both a state and an operator, which is actually kind of nice if you're physics, because it says you don't have to have two representations. In other words, I don't need to have a square dimensional matrix that's sparsely populated to express transitions. I can use just the same algebraic expression that I would use as a state, I can also use as an operator. So you can use them as either one. So realize that in my dissertation, I showed you what all those formulas are for the quantum computing part of it. And now we need to start spending more time on the standard model part of it. We're not trying to focus on the standard model transitions. We're trying to say something about the Higgs, which is the novel part of what we're doing. So just realize that we've showed how quantum computing operators create the Higgs, create the entanglement, and then those entanglement is literally, we showed you every formula here for how we create the Higgs and how we create the dark bosons and the dark matter. And so we've shown you all the math for that. And yeah, there's a lot more work to do about, showing you how three quarks form like a proton. Okay, and some of that is in the paper, in the appendix. Again, we're not focusing on the standard model stuff, but if we don't say anything about standard model, people are going to go, well, they're just waving their hands over that. Well, we're not. So realize that there's a lot of depth here. If I did a page per minute, a 45-page talk I was trying to compress a 45-page paper in 45 minutes, which is hard to do. So.
I have one general question. I hope you could
Sure.
briefly. So this work, one of the values in it is it offers a lot of insight. You run
Yeah.
Some of that insight corroborates the existence of particles that you've already found, but I think, if I understood you, it's also suggesting some they haven't even found yet.
Yes.
I think physicists would love to read this kind of stuff.
Right.
Are you getting any interest yet, or is it too early?
It's too early. I mean, we just produced the paper. We just released the paper in December. So that's part of the thing we're doing, is getting the message out. We sent this paper into one physics journal, and they says, what does this have to do with physics? And it's like, come on, really? I mean, really? It's like, so part of it is, if you have a recommendation about an appropriate journal that would be interested, referee journal, that we're self-published on our website, okay? We knew it was important. We wanted to get the message out. We wanted to tell the story because it's a novel way of looking at it. And so we still want to get a refereed paper so that people don't just write us off as a bunch of kooks from Dallas, okay? Okay. But the thing is, it's close together. It's self-consistent story. We can build these tools. We know every piece of line of code. I mean, this symbolic interpreter is less than 2,000 lines of code. It's not that hard. Okay? You just have to be consistent about it. And then you can run these searches, essentially exhaustive proofs. How did I prove the first time that Bell states are irreversible? I did an exhaustive proof in Perl. My early version of my tool was in Perl. And it ran again for a month or two, whatever it took, I don't remember. And the result of that was I proved that it was irreversible. You couldn't find something that would make it reversible. And once I knew that it really was that, I figured that was the case. Then I gave a closed form version of the proof that said the same thing. So we've proved it two different ways that this is true. But what does that mean to the physicists? Well, they should care about that. That's the story we're trying to get out. Right. So new that we don't have a lot of feedback. Part of it is we're just trying to get the story really clear so somebody can understand what we're trying to tell them. Okay, and so that's the mode we're in right now. So if somebody says, yeah, I really do. I like this idea here, or I don't like this idea. Yeah, let me know. Send me an email and say, yeah, I like to contribute something, and so.
Authors who used to participate in your PhysCom conferences, wouldn't they be interested in this?
Well, we announced it to the group, and there's some of the people who are long-term associates of Mike. There's Lou Kaufman is a topological algebra person from Chicago. And again, he's doing it from the purely math perspective. We're trying to do a combination of computer science, math, and physics. And part of it is it's so cross-domain knowledge that part of it is a lot of people go, huh? When I talk to some people here in computer science in the math department here that are working in quantum computing, they go, well, why would you ever stray from the standard representation of Hilbert space? It's like, then we have to work too hard to understand what you're saying. So it's. Go ahead.
I wonder if you have part of the proportion of
Yeah.
stuff,
Yeah.
dark energy,
Right.
your data mining and your classification of what you're finding in G4 spaces, those results respond to those other estimates of what's
Right. That's a good question. See, this here is very indicative that the dark matter states and the dark energy states are very common, and compared to like the Higgs and the Standard Model. So what we have to do is take this kind of bit count. This is the chance of this state occurring randomly, and how often it is, how often it occurs. And part of the reason why things that have a lot of singleton terms in it, like the dark matter has 8 terms in it, right? It's 4 times 2, 8 terms in it. So the more terms it has and the more variations of it, it's highly likely because there's a lot of permutations that will give you that state, right? And so we find out that just due to that kind of permutations that we see this kind of number. We haven't converted this bit count yet into, well, what does that mean? Essentially someone would have to do a simulation. We tried to do that, but we realized it would take more computing power than we have. But we tried to simulate the bootstrap of the universe where we just randomly have states, the current state of the universe, and have it interact with itself and start seeing what evolves out of it. We haven't done that yet. We'd like to do it, but that would give you, you can do it for G1 and G2 and G3. It's fairly straightforward to do it. But when you get to G4, all of a sudden you need a lot more computing power than we have. So.
Can you use this to estimate the weight of the Higgs boson?
Well, see, it turns out this bit content, you can map to an effective area on a black hole, because they know that entropy, 1 bit of entropy on a black hole is 4 times the Planck's area. I mean, they know that pretty accurately now. And that is equivalent to some relationship to the square of the mass. So, you could potentially turn these bit computations into an effective energy and effective mass. And again, that's really hard math. So if somebody has better math skills than we do, I mean, we're focusing on geometric algebra math skills. And part of the reason we're doing that is because we're not great mathematicians in the other area where the physicists are experts in it. So, if somebody's interested in helping us look at those questions, then we'd love to go look at it. Again, part of it is the experts in this field are so into their math. It's like all of a sudden we're asking him, here, come and learn something completely new and help us nobodies, with inventing, taking our insights and turning them into something interesting. There's some resistance to that.
So does that possible mapping from the states to the energies possibly direct a search for these possible particles that fall out of your computations?
Yeah. I mean, just continue data mining. There's all these states, all the bosons that we haven't identified yet what they are yet. There's 7,280. There's 12,000 unitary things. We don't know what all those are yet. A lot of them, see, if you have 2 bivectors that are entangled and a vector and a trivector that are entangled, any combination of those, a lot of these big complex states are the sum of those. So there's a lot of stuff that's just the sum of a bunch of entangled states. We don't know what that means yet. Right? So probably a lot of those things are quasi-entangled states of some kind. Okay. Well, great. Any one last question? Go ahead.
I have a question. You know about the physicists doing research, detectors, and particles. And how your research is correlated with that kind of detecting of particles?
Well, we've never seen a formula for the Higgs. I mean, it's transition. A lot of if you look at a lot of the Higgs research, at least the articles that says, well, this is the formula for the Higgs, it has to do with trying trying to quantize the energy formula. They're balancing the energy formulas to say, well, then this Higgs field must exist and must have this property. But they've not actually shown a formula for the Higgs particle like we are. So what we can say is, well, maybe our insight will help. Since we know that the E-bit states, the entangled states, our mapping matches exactly with what they do in the Hilbert space, except for these slight differences. The structure of it looks identical. So maybe if they believe us, well, if the entangled states look right, well, maybe they're saying something useful about the Higgs too, and we can think about that and maybe devise a better formula to go measure these things. So that's our goal, is to give them more insight that they didn't have before, because we're using this alternative representation. So, okay, great. Thanks a lot.